The time when we are dividing the time duration and we are hopping from one frequency to another frequency, we are spreading the frequency spectrum in terms of the time and also frequency at the same time. And the hopping gives us ability to have a sequence which is very useful, and we use that sequence for providing security for our communication. So this technology is associated with Bluetooth, and sometimes we wonder how that low power and that low cost is facilitating that transmission, and this technology is the answer for that question. Mohammed, I'm not able to remove the pool result. I don't know how it works, to be honest, but in next slide it will go away, hopefully. Yes, that's it. So today we are going to look at the signal generation, and don't worry about the slides, I have it on bright space. We are going to look at the signal generation, and before we move to signal generation, I have a quick comparison of the Bluetooth signal with infrared pulse. So many times it looks like Bluetooth is working the same way as infrared. And a very good example of infrared signal is the TV remote. If we look at two Bluetooth devices that are communicating with each other and the TV remote, for example, we can have this comparison between them. So we would say that Bluetooth is using the frequency, but for infrared communication, we are sending and receiving pulses. For the example, TV doesn't send anything back to the remote. Only remote sends pulses to TV to change the channel and so on. So that is the difference in terms of the type of the signal that is being sent. In terms of range, if we want to compare these two technologies together, because infrared is also very popular and has its own applications in IoT, that's why it is useful to have this comparison. So the range of Bluetooth from the classes we discussed when we were looking at the table of classes, if you remember. So we looked at different classes, class 1 up to class 4, and we have associated range for each class. What is the maximum range that we have here? So the maximum range would be theoretically up to 100 meters. It's hard to achieve that, but we would say that theoretically it can be up to 100 meters. But in terms of infrared sensor or infrared communication, or the example that I said, TV remote, what do you think about that? It doesn't go that far, maybe 5 meters, maybe a little bit more than that. But it is nowhere near Bluetooth can achieve. So if we look at the way that they are sending and receiving signals, there is something called line of sight. That means that two devices are actually facing each other directly, so there is no obstacles between them. That is called line of sight. You may have noticed that when you are controlling TV with remote, if there's something blocking the line between the remote and TV, the direct line, so you have hard time changing the channel. Well, that affects Bluetooth signal slightly, but it doesn't block the signal, because the way that Bluetooth devices are communicating is using different technology, and that technology does not rely on a line of sight. We know that any wave, including electromagnetic wave and radio wave, is affected by the path that they take from transmitter to receiver. But in case of using, frequencies and radio waves, is not going to depend on line of sight the same way that infrared sensor does. And about the rate or the speed that we can compare Bluetooth and infrared, we would say that theoretically Bluetooth can have a speed of 50 megabit per second. But for infrared sensors or transmitters, this rate is very small. So we are talking about kilobits. So that is a good comparison to have. Just if you hear that some technology is using infrared, and then I had one group of students working on a technology last year for IoT project, and they were using Bluetooth, and they were wondering why they can't use infrared. So if you have this comparison, then you know that in what application which technology is useful. Infrared has its own applications, and they are widely in use for IoT technology. Today we are going to look at the signal from signal generation point of view, and we say that Bluetooth is using a modulation called quadrature phase shift gain, QPSK. So I'm going to explain that, but before we move to QPSK, because that is a little bit advanced version of typical modulations that we have seen so far. Before that, I have to explain some basic digital modulations. So first we look at PSK, which is phase shift gain, and then we look at FSK, frequency shift gain, and ASK, the amplitude shift gain, and QAM. So QAM would be the quadrature amplitude modulation, and QPSK, which Bluetooth uses, is advanced version of the PSK that you have here. So when we look at the basic of this, then I can move and explain how QPSK signal works. Before I move on, I'm just reminding what is the difference between digital modulations and analog modulations. You remember a few classes before, we talked about analog modulations. Can you use the chat box to name two of them? Analog modulations that we looked when we were looking at Wi-Fi technology. Yeah, AM was one of them. What was the other one? Yes, FM. Thank you. And the reason we were calling it analog modulation was because the signal that was generated at the transmitter was in analog form, and we know that the carrier signal is also analog. So for that reason, we call it analog modulation. In this case, we are looking at the signals, the message signals, mainly data signal or message signal, or the signal that we want to apply the modulation on them. So they are mainly in digital format. Although the carrier signal is still analog, as we all know the nature of the signal is analog, but we call them digital modulation. In some cases, including QPSK and QAM, there is a similarity between the digital modulation and analog modulation. Later on, we will get to that point that we see that sometimes we can say that these are intermediate family between analog and digital modulation. So let's look at the PSK, phase shift gain. I'm sure many of you have had that in previous modules that you passed in school, but we are going to look at them quickly. So we have the modulation block, and then the carrier signal is generated, and many times we say that oscillator is generating that signal. And then we have our data or message that wants to be transmitted. And when we are looking at digital signals, we are looking at the binary sequence of that message signal, because everything is turned to ones and zeros. Now the modulation is going to generate this PSK wave, And the reason we call it PSK is because the phase of the carrier signal is being changed according to our message or data signal. On the right side, I have one signal that is 10110. Everyone can see this, right? So this data wants to be transmitted. Now the carrier signal is a typical sinusoid wave like this, and as I mentioned, one oscillator is generating it, for example. Now what PSK modulator is doing is changing this carrier signal according to these binary data. And if you look closely, I'm going to zoom in. Can anyone notice what is happening to this signal? So at this point, the signal is dropping from very highest point to very lowest point. So it is dropping from positive to negative. So the phase of the carrier signal is being affected. So at this point, you see that the phase is affected, and the sinusoid is not continuing its path. Let me use my annotation tool. So if it wanted to continue its usual path, it should have gone upward at this point and then coming back and going back this way. But because of the drop in binary, so it is inverted. Can you see the inversion here? And then at this point here, the 0 is changed to 1, or the negative value is hopping back to the positive value. So we are going to have another inversion in phase here. Later on, I'm going to explain about phase. What is the difference between phase and frequency? But for now, just keep in mind that the sinusoid is being inverted whenever we have that change in our binary signal. At this point, you see that the value of 1 is staying 1. So we don't have any change. And the way that carrier signal is being affected is by continuing the signal with the same phase. So we don't have any inversion here. Again, later when 1 is changed to 0, so we have this sharp drop from high value to negative value, and then the sinusoid is at this point, the phase is changed and the sinusoid is inverted. Later on, you are going to see how exactly that happens, that inversion, from mathematical point of view. If you want to read more, because I took these pictures from this reference, you can look at them. And if you have any question, you can just send me emails. The way that I'm going to examine this part is I'm going to give you plots, and I'm going to ask you to identify what kind of modulation is that. Or I'm going to give you, name the modulation scheme, and I give you the carrier signal and data signal, and I'm going to ask you guys to plot the modulated signal. Or I'm giving you modulated signal and the scheme, and I ask you to give me the data. So here we are looking at another type of modulation. It is called frequency shift gain. Here in this case, we are changing the frequency. It is slightly similar to FM, you might say, but the difference is here we have the digital data. So from block diagram point of view, we would say that the binary data is coming to two oscillators, and oscillators are very using the same signal, same sinusoid signal, carrier signal, with a slightly different frequency. So the frequency is shifted. That's the reason we are calling it frequency shift key, because we have a shift in frequency of the oscillators. And then they affect the binary signal, they are being affected by binary signal, and then the FSK signal can be generated. If we look closely to the plots, okay, so we have this data. It is changing from, if I use my annotation tools, it is changing from 1 to 0, or it can be from 1 to -1. Again, we have high value or 1, and then we have 0 here. Similar way that we discussed about FM modulation, here the carrier is going to change when I have change in the data. So in this case, I'm using a slightly higher frequency for transmitting ones. As you can see in this boundary here, the frequency is slightly more than this one. How we can see that? So in this boundary, I have 2 peaks, but here I have like 3 peaks, 3.5. I would say 2.5, 3.5. So if I'm looking at the F1 and F2 here, so my F1 is a slightly higher than my usual, the regular carrier frequency. And then when I'm changing from 1 to 0, I'm using a slightly lower frequency for my modulated signal. So the way that we look at it is this boundary. If you look at this carrier signal, if you want to see how frequent it is happening, so we have again 2.5 peaks here. And as you can notice by comparing this boundary, the white boundary with this one here, so you would say that here I have 1.5. So it is shifted according to the data. Again, it is going back to 1. So I'm going back to the frequency that I had for ones, and then goes back to the lower frequency. Please note that here I'm using 2 frequencies, okay? I have F1 and F2. These F1 and F2, they vary from the initial carrier frequency. They are slightly different. One of them is slightly higher, and one of them is slightly lower. If you want to read more and if you want to do a research about this topic, you may find that we have a variety of this technology. So this is the basic. Now, another type of digital modulation, or let's call it keying techniques, is amplitude shift keying. So here we are going to look at the amplitude that can be shifted, but the way that we look at it is slightly different from AM modulation in analog modulation part. So here when we have the binary data, if I want to zoom in, so if I assume that this binary data wants to be transmitted, I'm changing the carrier signal according to that in a way that when I have 1, I am sending the signal, but when I have 0, I'm sending nothing. Again, when I have 1, I send a small portion of the signal, and then when I have 0, I don't send anything. So it is sending the tones of a signal according to the binary sequence that wants to be transmitted. A very simplified explanation how from hardware point of view that can be implemented. You may use a switch type technology or something like flip-flops that lets the sinusoid to pass only when you have voltage. That's not exactly how it is implemented, but it is a good way of looking at how it can be implemented, how that signal can be generated. So I have control of my sinusoid only when I have ones, and I'm allowing it when I have ones, and when I have zero, it is blocked, so nothing is sent. The next type of modulation is QAM, quadrature amplitude modulation. This is a very popular scheme, and we see many telecommunication systems and technologies that are using it these days. And mainly we use two signals to send any data message. Before I explain the QAM, and also that leads me to QPSK, I'm going to explain something called in phase and in quadrature, or I and Q. And normally we refer to them as I and Q. It is very important to learn this basic because I'm going to look at constellations. We call them constellations. And they differ in terms of shaping them, and I need to explain the mathematics that relates them together. Have you heard about I and Q before? You can use the chat box or turn on your mic. Has anyone heard about I and Q before? In Wi-Fi class, Andres. Perfect. I'm not going to have lots of details, just to explaining it and relate the modulations. So I'm explaining it from very basic, but at any point, if you find it confusing or you need me to explaining it more, please just use the chat box or turn on your mic and I explain it further. If you look at a sinusoid wave, a very typical format that a sine wave can be represented would be like this one here. So we would have a cosine of 2 pi ft plus phi. Should I say phi or phi? Correct me if my English is not good. So this is a typical sinusoid. We use cosine to represent the typical sinusoid, but you know that it might change by changing the phase. So the A would represent the amplitude of that wave or signal. Many times I use wave, many times I use signal, but I'm referring to the same thing. And then the F here would represent the frequency of that. And the phi or phi here is representing the phase. And we have two other types of representing the same thing. One of them is the vector form. So vector form, we are looking at a point in vector format. So if the same sine wave can be represented as this dot here, so the distance that this dot has from the point 0, 0, that would be considered as amplitude. So the amount of the distance from this point to this point would be A. So the image or the shadow on this vector here would be considered as I, or in phase, and then the image or the shadow of this point on this vector here would be considered as Q, or in quadrature. Now we want to see how this I and how this Q can be written mathematically in respect to that generic form. So if I have that here again, so from a time perspective, I would say that IT is equal to MT cosine of phi t, and then QT is equal to MT cosine of phi t. So the phi t is referring to the phase, and these two are the images of the point that I'm representing here. Another way that I can represent the same sine wave is from polar point of view. So I would say the polar representation of instantaneous sine wave is mt with angle of phi t. So this is very important because we are going to change that phase and see how that makes a modulation work. So if I want to look how exactly from Cartesian point of view we can convert them to each other, so I would say that if I have a triangle here with 90-degree angle, and my theta angle is here, if I say that this one here is x and my y is this distance here, and I have the r to show this distance, and this r would represent my amplitude, and x and y would represent the I and Q. I'm just reminding it from mathematics with different variables, so hopefully that makes it a little bit easier to understand, but feel free to interrupt me if I'm not explaining it well. So from Cartesian point of view, we would say we have x and y. From polar point of view, from polar perspective, we would say we have r and theta, and the relationship between them would be this conversion that I have here. So x would be equal to r cosine of theta, and y would be equal to r sine of theta. And then we have this relationship. What is this relationship called? Anyone remembers? Yeah, that is from high school, yes. Yeah, so it is a square root of x and y, and that will relate us to how to calculate the theta. Yeah, I'm happy that you all remember that part of mathematics. So going back, look at this formula here, the way that we have the cosine and sine. So you can understand how exactly I'm talking about the images. So here, when I am dividing one point in polar format to I and Q, I have two different signals. Okay, I think I made a mistake here. One of them should be sine. Let me check my notes. I'm not mistaken. I made a mistake here. Yes, I think I made mistake, and that one should be sine. Let me check that, and I fix my slides there, and I put the updated version on the bright space. But what I mean is, has a mistake, QT. Yes, I think I made a mistake for that. I should have put sine for that. But anyway, what I'm referring is I have two signals. One of them is cosine, another one is sine. And you know that the difference between sine and cosine is the phase, the angle. And by adding some values to the phase, I can convert one to another one. How much should I add to the angle to change cosine to sine? Anyone remembers? Well, Abdul Rashid is saying 45. What other people think? Yeah, use the chat box. Yeah, take your time. I'm waiting. I want everyone to type this in Google. How to convert sine to cosine, and see what comes up. The answer is not 45. I want you to find out what is the angle that should be added to a cosine to convert it to sine, or vice versa. Yes, convert cosine to sine, yes. Sherry, any idea? Yeah, that's it. 90 degree. That's the answer. Thank you, Eric. So by 90 degree addition in phase, we can convert them together. So that means that if I have one oscillator that is generating my cosine, if I have a shift in the phase, I can have another signal generated. That helps us to generate QAM and QPSK signal. Now, if we look at the INQ format again, this point here is called constellation. And I'm going to look how constellation can vary, can differ if I change the phase, but I keep the amplitude or magnitude the same. So I'm saying the absolute of I is equal to absolute of Q. So I'm saying that amplitude is not being changed. And the only thing that is changing is my theta. Right now, if they are equal to each other, I will have the theta is equal to tangent inverse of 1, and that is equal to 45 degree. So If I want to change that by changing the 90-degree angle only, all right? So I'm allowed to add or subtract 90-degree angle from this face. What would be the next constellation? Anyone wants to take? I'm going to turn the whiteboard open. Please don't start doing doodling all over. But if anyone wants to take the marker and explain, turn on the mic and explain how that differs from this point, when the next constellation would look like. If I have two signals, one of them is being transmitted using this constellation here with this angle, what the other constellation would look like or will take place when I add 90-degree or I subtract 90-degree. I turn the multi-user whiteboard on, okay? Any idea? Abdurrashid is saying, say that again. Okay, I'm saying that we looked at the way that one point sine wave can be represented from a polar perspective and from a vector perspective. Now, looking back to vector perspective, I want to change the phase, right? I want to change the phase by adding 90-degree and subtracting 90-degree. Glenn, you need to know how things work, okay? You may not need to remember all the formulas, but you should be able to know the links and you know how they associate with modulation. So anyone wants to take the marker and draw it? Who drew this line? I missed it. Craig, do you want to? Paul, I think. Okay, Paul, do you want to do it? Pierce is saying the same. Do you want to turn on your mic and say why would it be the same? I am adding 90-degree to this angle. So if someone is saying that the point will be mirrored this way and it will come all the way here, that would add 180-degree. Yeah, that's correct, Pierce. So that wouldn't be 90-degree. But if I'm doing that, adding 90-degree constantly, I will reach to that point. How that happens is, let me get my tools. Now, if I'm going to the left side with 90-degree addition to this angle, so I would end up somewhere here. And then I imagine that maybe I should do a little bit better job by drawing 90-degree angle here. Yeah, so not really. I want to say that angle is 90-degree. So this angle here between my red line and my green line would be 90-degree. And I end up, Cray is asking the questions. If you missed the tutorial section, we discussed how to get the exam papers from last year, and it is available on library website. And if you want, you can ask your friends about the username password that works to get done. So the point will look like this here. The next point, I'm changing only 90-degree angle for this constellation. Now, if I keep going, if I add another 90-degree, I will end up the place that your friends draw here. So if I have another 90-degree here, I will end up somewhere here. And then if I keep going that way, can someone draw the next constellation point? Any volunteer? So if I keep going, Abdul Rashid, do you want to take the marker? Okay, the whiteboard is open. Abdul Rashid, go ahead. All right, that didn't work. Yeah, it would look like something like that. So it will have another 90 angle, and then I will have my constellation point here. And then if I add another one, another 90-degree, I will come back to my original place. Is it clear what I'm explaining here? Yeah? Yeah? All right. So this would be the representation of I and Q for a very simple modulation. And in this scheme, we are changing only angles by adding or subtracting a 90-degree angle. We discuss further in next class. We are running out of time. I'm just going to share the attendance sheet. If you have any question about things that we discussed today, use the chat box or turn on your mic. Okay, thank you everyone. If Hamid Azerbas is here, do I have your permission to publish this video on YouTube? Because everybody else said yes. Is everyone happy I publish it on YouTube?